It must be me. Good morning to you all. Can I just do a quick show of hands, get the audience participation thing in right from the start? Who here is Abate or ex-Abate? Oh God, I don't need to introduce myself. You came back to see me. Okay. Those of you who... I've got one of those little I'm back badges, you know, it's just, this ain't my first rodeo. I think it's the 7th security that I've spoken at. Rory McEwen is claiming his 8th. I think he's trying to claim precedence at the moment. I think it's my 7th one, please. You will know, if you've been here before, if you're a returner to security, but what happens is that the Programme Committee of Security, round about a week before security, suddenly start shitting themselves. Ian, one of our speakers has dropped out. Would you mind standing in? So hence I am Deputy Chief Acting Standard Emergency Replacement Vice for the Dog and Speaker. So you got that. This year, however, it was even more nerve-wracking than usual for me, in that I kind of went, I've got nothing on the books. It probably means I've done nothing interesting for the past year. I've been too busy teaching to do anything. Oh no, sorry, teaching is interesting. You've got to remember my own. So the upshot of that is, what I thought I would do is, I'm actually going to talk about some work that was done by James Sutherland, who was one of my PhD students here. So it's not actually something that I've done myself. So when you ask difficult technical questions in about half an hour, I'm going to go, I don't know, ask James. But you never know, I might be able to do it since I supervised it, along with Natalie, who I'm sure you all know as well. So, having got the kind of silly introduction out of the way, what are we actually going to talk about? How long do I have, by the way? How long is this session? When do you think? An hour! You actually volunteered to come and listen to an extra hour of on the creation of a secure key enclave. So what this is about managing how you keep hold of your encryption and decryption keys without anything bad happening. Via the use of memory isolation, so trying to reserve a block of memory in the PC somehow and saying, I can use this to read and write my keys, you lot cannot read and write this bit of memory. How do we chop a bit of memory out of the PC and say, only I can access it? Well, we use a thing called Systems Management Mode, which kind of dates way, way back. I think I first came across Systems Management Mode in 19. Okay, let's not worry what came after the 19. The fact that it starts with a 19 will tell you how long Systems Management Mode has been kicking around. If I was really pushed, I think it first emerged on a 386 processor, so I probably saw it around about 1989. Don't know. We'll tell you what it is, why it's important, and why it might be fun to play with. As you can tell, I'm giving this talk somewhere else, and for that reason I put on where the University of Abate is. Since we're all here, I suspect that map is superfluous today. Let's not worry about that. Okay, we've done what have we done? We have built James built it, we kind of always do supervising. We built a secure key store. Now this is the fun bit, this is why I think this is actually interesting. Is that we use only commodity hardware and the existing facilities in the x86 architecture. You can do what I'm talking about. You can do key enclaves very, very easily with a bit of dedicated hardware. SGX, TPM, other abbreviations you may have heard of. You can do it. Turns out it's actually possible with just a processor and nothing else. You might need to replace your BIOS, more of which later. We built it. We evaluated its functionality. Does it actually work at all? Is it secure in any sense? Well, it's a bit better than not having a secure enclave, and we evaluated its performance. Is doing this going to slow us down so much that actually it's pointless, useless, and just painful. All right. So what I'm going to talk about, I'm going to spend a while talking about why I think this is a problem, and why I think this is a moderately interesting problem to have a go at. I'm going to talk a little bit about SMM, Systems Management Mode, on the i386 family. I'll say a little bit about the experimental evaluation. So there's kind of three phases to the talk till we get to the pull the rabbit out of the hat, does it work business. So the problem is basically keeping crypto keys safe while they're in RAM being used. I don't think I've ever had a standing audience where there was people standing at the back before. Guys, there is some room down at the front here if you want to come and don't feel bad about interrupting. Bring yourselves down the front, grab a comfortable seat, and don't sit there at the back. Folks who are sitting just at the ends, if you want to push in a bit and let folks in, that'd be great. Okay. So, time for some of my bad artistic skills. Those of you who were up here in this very room back in around about 1911, even I wasn't here in 1911, 2011, 2010, will remember some of my lectures. The first one I used to give at the time were famous for my extremely bad drawing skills, which is why I stopped doing them. And yet I thought a cartoon was possibly the appropriate way to do this. So this is the use case, and the use case is verification of key. So what's going on here? Let's assume that we're on a PC and a document arrives. Maybe we requested it from a secure web server or whatever. A document arrives, could be an email, could be just about anything. It's encrypted with my public key. Great, we know about public key and private keys. We know that if it's been encrypted with my public key, in order for me to read it, I'm going to have to decrypt it. Now, where am I going to get my private key from? Are we going to ask the user, am I going to type a 4092 byte secret key in every time I need it? Answer, no, even my memory, especially my memory, will not cope with that. If it was an 8-bit key, I probably still wouldn't remember it. Rather embarrassingly, 10 minutes before I gave this talk, I was up in Rory McEwen and Ian Smart's tutorial up in 4511. Of course, the first thing they ask you to do is to log into the Wi-Fi and access this. Ian, what's your password? Oh shit, I changed it last week, I have no idea. Instant password reset, instant fail of QDOS as cyber security. Okay, so asking somebody to type in a secure length of key is probably not a bad idea. Maybe it's stored on disk. Well, there are risks associated with that, but we're all security professionals here. Let's assume that we've managed to store our key somewhere securely on disk. That's fine, that's good. Couldn't tell stories at this stage about the very first time I saw SSH and its key management thing. Technician came in at another university which I remain nameless, installed all this wonderful stuff on my PC and said, "There you are, you're secure." Fine, great. What were all these files? Private key, public key? No idea. If somebody had come in that day and said, "Can I have your private key file, please?" Yeah, sure. Nobody explained these things to end users. Maybe there's a lesson to be learned there. Anyway, I digressed. My private key, wherever it came from, is going to end up in RAM. Because if we need to run a program which is going to use that key to decrypt something which has just arrived, we're going to have it. Or does it? Maybe there are ways around that, but that's not the scope of this too. Well, that should be fine, except somebody appears to have used a hammer. Maybe it's a hammer. They have managed to access something from inside RAM that they shouldn't be able to access, and here is, I don't know, is that common claim? Running away with my key in his knapsack into his glorious retirement. Good luck doing it. That's fine. So just actually having the key in RAM makes it vulnerable. Okay, I know we've solved Rowhammer, but there'll be something else, actually. So keeping it safe whilst it's in RAM is actually a genuine problem, I suggest. What we would like is actually this situation. So here is my RAM, here is a castle, and here is the Holy Grail, or in fact my private key, stored somewhere in an enclave inside that RAM. Even if this guy can do a roll hammer on my machine, and the battery is failing rapidly on my laser pointer, resort to all technology, even if he's able to break into the RAM somehow, the key is still safe in the enclave. Can we do that? Is there a way of doing that? Was the name of the game here. So that's the motivating use case of what you're about to see. Now I have to take you back to first year to CNP 101, where we talked about operating systems and we talked about virtual memory systems. I'm sure you've all, whether you have a tape on or not, you've all seen the idea of a paged virtual memory system, whereby the memory space is mapped somehow on the disk, and miraculously your machine appears to have more RAM surely. What I hope you will remember is those pages of RAM are kind of almost randomly intermingled. So we've got pages belonging to the operating system, pages belonging to applications. Fine, they're all mixed up. Now, theoretically, the way these things are set up, the way they're meant to work is that if you're an application and you've been given access to that page of RAM, then you should not be able to touch the pages on the side of you, unless they're yours, of course, so you might have contiguous blocks of RAM. But if they ain't your pages, then you're not meant to be able to access them. And that is why, that's where Rollhammer and its like are so particularly damaging and dangerous, that it relied, I don't know how much you've ever read about Rollhammer, but it relied on I liked it. It was a hardware attack. It was based right down at transistor level. And it relied on some kind of unexpected interaction between physically close memory cells, literally in the RAM. It allowed you to kind of, by rapidly changing the address in a certain way, it allowed you to access things which weren't in your page of RAM. And in particular, I think they demonstrated using to do privilege escalation by reading stuff in the next adjacent page. I can't remember the precise details of it. Please forgive me. Rollhammer was some years ago. Well, that was a consequence of system pages being intermingled with low privilege application pages. It allowed that low privilege application to actually access something that it shouldn't have for something high privilege. Similar kind of idea with kind of hypervisor escape, being able to read outside what you're meant to be able to read. The takeaway message from that slide is, if my encryption keys, my precious public key, is stored somewhere there in RAM, then it's vulnerable to this kind of attack. RAM can normally be considered secure. Page separation, process separation, are no longer sufficient just to keep your keys secure. That's a slide which I stole unashamedly from Wikipedia, and I now can't remember why I put it in. It's meant to be an illustration of if you can legitimately access that cell or that set of bytes that with Rollhammer you could hop down and read something else. All of the attacks were kind of dependent on things being co-located in memory or very close to each other. Never mind. So it's a known problem. There are known solutions to it. There are ways of doing key enclaves as it is. Theoretically, process separation and process isolation should provide that. But when you're going underneath those things, these are operating system concepts. I suggest to you that the hardware and chip level stuff is beneath the operating system. So what Rollhammer did was very straight with the operating system code, or all your data are belong to us. Okay. People have looked at things like RAM encryption, whereby anything written to RAM is actually encrypted before it's stored there. Great, it works. The downside is everything's got to be encrypted and decrypted. When you use it, you are slowing the whole thing down by I can pull a statistic out of the air. Honest answer, I don't know what the source is. Another possible approach has been address space layout randomization. You are used when you think of addresses and pointers. Do you think addresses and pointers? Do you lie there at 3 o'clock in the morning thinking address, pointer? Do you do C++ in your sleep? Oh, I thought I was normal. All right. The idea is you're used to one address. If you've got address 5, we're kind of used to the next address next to it being 6. What if it wasn't? What if it was AFX27B? AFX, that would be interesting. AFX27, that's not even a valid hex address. Okay, we're used to that for being 6. What if it were 27? Okay, so we can actually randomise the layout of the order of those things. So, okay, I can read the next cell. That maybe doesn't actually get me much in terms of being able to understand what I've got. There are things out there to do with swap encryption, virtual memory system. You know that pages end up out on disk in a swap file. Forensics course with me and all that stuff. Okay, what happens if we actually encrypt the swap file? Well, it stops people accessing by going via that file for things, so that's one way of doing it. We've got the good old operating system things we've been dependent on. Virtual machine isolation. If you're doing something in one virtual machine, you certainly should be able to see something going on in another virtual machine. But we know about hypervisor attacks. And we've talked about the other two hardware solutions where basically you have a dedicated chip which you put keys in, and somehow you lock it. And only your program, your trusted program, can access those chips. So that was the state of key enclaves. We observed, James observed, and then mentioned it to me, and I went, oh, that's interesting, that there is a concept in PC architecture of SMRAM, System Management RAM, which is exactly what it says on there, a block of the standard system RAM, DRAM, that can only be addressed by the processor. Wait, hang on, memory can be accessed by something else other than the processor? Well, yes it can. Direct memory access, DNA attacks, the idea FireWire attacks from several years ago now, you plug in a FireWire device and it was given direct access to the memory bus. Okay, well, first thing, system RAM, system management RAM is only accessible by the processor. All of the other devices that might access memory cannot touch it anyway. But it can only be addressed by the processor when the processor is in systems management mode. Okay, so what the hell is systems management mode? Oh. Your PC, thank you, Mr. Gates, looks a lot like this. You have the processor core, you have a thing that controls the actual access to the RAM. I called it decode logic years ago. It's got a bit more complex than that these days. We might call it the memory controller, connected to the processor on the address bus and the data bus, and a couple of other lines down here, the names of which are extremely obscure: SMIACT2 and D_open. Right. If you look at the memory space in your PC, so it starts at location 0 and goes up to however many gigabytes you've got installed these days. At round about there, well, in fact, not round about there, exactly there in the memory space, you'll find that there are two completely separate banks of RAM which actually occupy the same memory space. So multiple cells of RAM with the same address. Bit odd. Turns out you can turn those two on and off with these lines. When these are, now I can't remember whether they're active high or active low. Let's call it true. When they're true, the SM RAM block, just this block of memory, appears in that address space. When they're not true, it's actually part of the video RAM. And actually that dates back to Bill Gates, and you'll never need more than 640k of RAM in any PC. Circa 19, not a lot. So in other words, we can switch those two out. And it turns out that system management mode which controls those two lines, and therefore which one of those two is actually connected to the memory bus. So the idea that we have goes something like this. We would like to reserve that bit of SM RAM, and that it's only going to be available while we're in systems management mode. And what we're going to do is to put into that area of RAM two things. Now, this is the important bit. The keys, the private keys, are going to live in there. Also, so does the code which allows you to access them. Oh, well, that's actually interesting. So if the code's in there, and that's locked, well, I can't change the code accessing the private keys. That's got to be interesting and worthwhile playing. Okay. So the idea is that if you want to go in here, if you want access to this, you've got to actually switch the whole system into system management mode via a syscall. And again, we're getting down to the low-level assembly programming here. You go to that mode, you can access that RAM, you do whatever you've got to do, you exit SM, back out to user land, and everything's happy. So for some brief moment, we were able to access these things. So the idea is that when you boot your system, you negotiate the keys, put them in there, code in that you're going to use to access those keys. So there's going to be routines in there for, okay, validate the certificate, generate the key, all that kind of thing. That's it in there. Once that block of RAM is locked, we know that code is locked. That's the only key, that's the only code that can access that. We have some degree of safety going in. I think I've just said this one. So the overall operation, we do key negotiation during some startup process. We then transition into SMM. Boom, it's locked. We've got our keys locked away. Nobody else, other than system management mode code, can actually access those things. So the overall architecture that we built was something like that. We wanted to have things like verification and signature functions available. If we need to put stuff into here, we inject it into a 4K RAM page, which is also accessible from there, but is not inside the Enclave. We perform the entry call, which we can go in here. We do whatever we need to sign whatever's going in there using these private keys. When we're done, we exit, we're out. The keys never exit that thing, so they're never out, available to the general public. Meant to be good. So, that's a kind of generalised technique. I could go into great detail about what you could use those keys for. Anything you use a key for, this is the meaning of it. So, there's a whole variety of authentication, crypto fundamentals, operations that we could implement in there. We chose to demonstrate it with just one, signing something. What did we actually do? Well, to prove that this stuff works, we built a secure web server, obviously. So it came in one morning, Monday morning, void name. No, we didn't. We found, I can't even remember which web server it was, but we basically took an existing web server and we bastardized it to obtain its keys and to do its signing via this method. Now, at this point, I've got to go back to what I said earlier about you might want to replace your BIOS. Turns out that the normal BIOS doesn't do the shifting over to the mode when you want. We actually had to create our own BIOS. And again, we came in one Monday morning and started writing assembler and made our own BIOS. No, we didn't. There is a freeware BIOS you can download. We actually did all of this, or most of this, on an emulator, so we weren't actually burning BIOS chips anywhere. But that was kind of interesting when I suddenly realised, oh yeah, we're going to have to create our own BIOS for this with different functions. So there we are. Can we build a web server which can prove its identity to something else, to your browser, by signing responses with keys and code that were stored in that enclave? We ask ourselves 3 questions. 1, does it work at all? 2, is it secure? And 3, is it fast enough? That's not the best choice of colours, Ian. Apologies. Let me tell you about the 4 tests that we did. First of all, we just used it with a range of browsers just to see whether it worked. Secondly, we ran it through the Qualys SSL Labs verification page to see whether it liked the information it was getting back, whether it thought the keys were even valid. Thirdly, we did some micro-benchmarking. So we're actually measuring the time that some very, very quick routines, like going into systems management mode and coming back out again, how long did they take? And were they going to be so slow that they would mean this technique is pointless? Finally, tests 4, A, B, and C, we compared the performance of our web server with 3 different levels of protection. So we compared, as a baseline, how fast can this thing serve web pages anyway? Secondly, how fast can this serve web pages when the only kind of protection we're using is that the encryption and decryption process is handled in a separate process, so process-level separation. Finally, we did full Monty. Can we serve pages where we're actually doing the checking the certificate using the technique that we've got there? And of course, we timed all of this to see what happens. So first one, does it work? Yeah, it works. We tried it with a range of browsers. Pick your favourite browsers. We tried however many of them. They all said, yeah, your SSL stuff that you're sending backwards and forwards is valid. We understand it. You've got your basic programming right. Big deal. We tried it against the Qualys SSL labs. That gave us 3 greens. So you're responding to the protocol correctly. The key exchange is correct. The throughput seems appropriate. Can't remember what the red T is, ignore it. That was something completely not to do with what we were doing, but ignore them. This is the big one. We spoke about address randomization, we spoke about encrypted memory. You say, well, look, that's basically too slow to be of any kind of use. Is this practical? Alright, so micro-benchmarking. We did some real-time measurements of the transition to and from system management mode, because if you're going to do this, you've got to put the computer into system management mode, do your decryption, get back out of system management mode. How long is that going to take? And then we did our web survey just to see whether this actually goes. So the micro-benchmarking, we're going down into some detail here. My apologies if this gets a little bit tedious. First thing we measured was simply the round trip to and from system management mode. We went into systems management mode, we did nothing, and we came back out again. Okay, how long was that? We did an open and close of a file in systems management mode. We did get a call, which basically is it's kind of the simplest call you can make into the kernel in this mode. And then finally, can we execute some kind of cryptographic operation? Specifically, can we generate a signed certificate? All right. We tried it on a number of different machines. We tried it on a... Can I remember what these are? X200? I have absolutely no idea. It was 2017 when we did this. T60? No, probably all Hewlett Packard stuff. It's the University Enterprise Hewlett Packard stuff. And then finally, we did it with a QEMU virtual machine. So there's the different processors. There's the clock speed. It's in the virtual machine. That clock speed roughly comparable. RAM, yeah, didn't have too much. The Lenovo even says it's a Lenovo laptop. Yeah. Bias. So we had to, with this one, we did, that one it worked okay. That one I think we had to mess around with, and that one is can't recall. Is that the default one for Quenu? Can't remember. At least one of those we had to fiddle around with to get it to go. Did it work? Did it work? So what happened? No operation, so simply getting into systems management mode and doing nothing, 448 microseconds, not milliseconds, microseconds. Oh, actually, that's that. So on that machine, it was that. On our virtual machine, we ended up with that, and that's multiplying over thousands of operations. I can't remember. Thousands of all right, so we've got a baseline case. Let's do our simplest get head operation, microseconds, 1.4 microseconds. All right, so this isn't bothering us too much. We'll not worry about the open close. Finally, we get down here, under a millisecond to do the signing operation. I'm quite impressed at that point. Actually, this isn't too much overhead at all in terms of what we're doing. That gave us some confidence to kind of go ahead and actually try it with some real world stuff. Now then, every time I come to this slide, I've got to pause and think exactly what does this one mean. So this is the execution time rather than in real time. This is measuring it in ticks per second, clock ticks. And again, it's really just comparing. The absolute values don't mean very much at all. But it's comparing it between the basic do-nothing operation across the different machines there. So that possibly doesn't tell you a great deal. That's just simply serving as a comparison between the different controls that we were using. Where it got a whole lot more interesting is when we started testing the speed of page serving with our different levels of protection. So again, we're going to do it with no encryption, with process separation for keys, and with this one we invent the full SNN isolation. What did we actually do? We fired HTTP requests at this poor virtual machine in QEMU generated via curl. We did it with some different sizes of web pages. So you can see small web pages, you're doing it a lot, and there's a lot of repeated stuff going on. For larger web pages, while you're only kind of popping in there once to do the certificate validation and then back out. So doing it with a variety of page sizes, we thought gave us a kind of trial of a realistic thing. Right. Requests per second, size of response. Each one of those, we've got the 5 different tests going on here on the different machines and the different cases. The interesting one to look at is Q2. That's the one with the full system you used to do it. Okay, small pages, our system, we're managing to service round about 500 requests per second. Without our stuff, we were doing up in that 1,000 to 1,500. Yeah, it's slower. Dare I call it about half speed? No, actually, a security technique that reduces the speed of something by half. I don't know, is that good? Is that bad? I could just wait 18 months and let Moore's law do his stuff. I don't care about that. So actually, we're going to count that as a success. We thought that's pretty useful. That's small web pages where we're kind of repeatedly doing our crypto operations on. As they got larger, well, actually, you can see that our other scales of protection, so this was the one using process separation protection, this is the one with our SNN protection. By the time you get to a 1 megabyte page, there's no difference between them. So again, as things got bigger, things got better for us. we're going to call that a success. You were expecting a 1 hour talk, weren't you? You better have lots of good questions. There you go. The conclusion of all of that, the work that what James got his PhD on, was that we accepted his hypothesis. The SMM technique offers greater key protection than process separation, with a minimal impact on processing speed. So halving the speed of something is now officially a minimal impact. There you go. That's what we did. We've got a way of keeping the keys safe that doesn't need special hardware. I hope that's so interesting. Would anybody like to ask any questions about all of that? James?
Yes. How does this compare to like the house of Kerberos and other mechanisms for key exchange?
That's a reasonable question. Kerberos is basically, dare we say that's protecting the keys in transit?
Well, it's a certificate, so you get it. You know something, you get a ticket.
Yeah, I put it this way, I'd be interested to see somebody have a go at Kerberos with something like Warhammer. I'm not aware of that ever having been done, so it's kind of nobody's really broken Kerberos.
Sure.
Theoretically, it could be done, whereas this would be proof against it, and that would be the only reason you'd want to do this rather than taking a certificate-based approach.
Yeah.
There are It's one of those things. If you've got a system where the key ends up in RAM for any length of time, then theoretically it's vulnerable to that kind of attack. Theoretically, this will protect against it. So from that point of view, I'm going to say that it does something that Kerberos does not do. Better approach may well be don't keep the keys in RAM for them. Well, yes.
How does that method stack up against more dedicated security?
Again, good question. How does it stack up against a more dedicated hardware security module? I am not aware that we've actually done any likewise performance tests on the hardware modules. Somebody's looking for a good MSC project. That would actually be very interesting just to see what the comparison time-wise is. Honest answer is I don't know. That's a valid. Yes.
So what do you think the lifetime of this technique is? Based on the fact that BIOS is on its way out and many modern machines don't actually have a BIOS.
It's true. I think what we've got to do is differentiate between the implementation of the idea, which is profoundly based upon BIOS and swapping between these modes. I'm actually looking at the new hardware architectures and saying, what do they have in terms of the equivalent of?
Yes, because the modern thing or the equivalent of modern would be SGX.
Yeah, exactly. Yeah. Which is the modern thing to look at. It was. I suppose the interesting at the time, and I have confessed this was 2017, so I'm not exactly reporting right after the minute working. It was something that you could virtually use tomorrow if you wanted to provide protection for your keys without replacing the entire stock of machines that are out in the world. Then it was, possibly interesting. Worthwhile noting that ARM chips have something similar. So, if you want to do this kind of thing on your phone, again, somebody wanted to implement that as part of their MSC project rather than build it, might be a very interesting new project. I'm not saying it's done wrong, but it has an equivalent systems management mode, which might be something that will work.
It's multi-threaded part of this operation.
No. Okay. So maybe it should have been at the time. No, it wasn't. It's. I mean, this is so typical PhD work rather than serious things that ethical hackers really do. There's an idea. I wonder if we can prove whether there's anything in this idea. Yes, we can. Did we look at it on the multi-threading element?
So Rowhammer was having access to a low privilege bit of RAM and accessing the other side. What sort of privilege restrictions are there in entering systems management mode? This is only protected so far as systems management mode.
Yeah, okay, so the question is what is systems management mode vulnerable to Rowhammer is what I'm actually asking.
If you can access the system management mode, then you can kind of have this access to same address.
The answer is no, you can't, because of that. If you remember that slide where I have those two control lines.
Yeah.
You can Rowhammer all you like up around, unless those cut lines are being held high by being in systems management mode, then you physically cannot touch that RAM. So in that sense, it's resistant to it. If you could, I dare say there's some kind of waste to the modern thing going on here, if you could get your Rowhammer thing to fire in before you've actually taken those blocks of RAM out, before you block the current systems management mode, then yeah, I dare say you could get around that way. My understanding is that Rowhammer actually required longer to do its stuff. It wasn't really a good one for doing race condition stuff. So it's somewhat resistant, but again, the clever thinking should be trying to go around. The arms race is there. Think of something and then think about how to destroy it. Any more for anyone?
You know between this and the data side is usually I hear there's data management, data use, and data rest. And data at rest in transit is useful. But then these kind of look like, okay, it's like in use, it's in memory. Would something similar be?
It's the same kind of idea, but what you're looking at is the class of attacks. Not strictly Rowhammer, but that class of attacks where you're using the hardware and you're going underneath that, and you're actually subverting the whole business of it being at rest anyway. You don't care that it's at rest, it's there. The internal under that by using our hardware dependencies, so we're under the level of the operating system, but all the things that might be providing your security at rest, simply kind of went under that protection, which was what we thought was interesting. And was there a theoretical protection against something that was taking that tunneling under route? Well, there is, because there's these 4K pages of RAM in which you can actually physically remove them from the address space of the machine. It really does all go back to that one slide. That one. It's the fact that RAM, where you're storing whatever you think is value, can physically be disconnected from the rest of the machine. We could not easily see a way whereby that could be subverted, so for that reason we felt the case in
If you're repurposing this existing block of SF RAM, are there space concerns with how much you can actually do in it?
Yes. As you can see, it's that size, it's not a lot.
You're taking 4,000 size keys.
You've instantly got a limit on the size of key you have, which is not good. It's what it is. We're not pretending it's the answer to the universe and everything. It's an interesting exercise in thinking down at the lowest of hardware levels and seeing what protection that kind of thing can offer you.
Just to drill on your point, this slipping underneath is actually valuable attack things.
Yeah.
Bring your own operating drive, for instance, because it is not that.
Yeah.
It has recently been used, so I think the problem is still valid.
Okay, well, it's good to hear that we occasionally get things relevant in my campaign. Okay, that's a bit earlier than I was going to do, folks, but short of any more questions, one more question.
Do you think using the state you use what you're saying that you could store something that's the system management that you don't want to be found?
Can you store malware in systems management mode? Yes. Yeah, that'd be interesting to see. I'm not seeing anybody do it, so somewhere really hide stuff can't be accessed by the rest of the system. Yay!
As long as it fits in 4K.
As long as it fits in 4K. You can fit a reverse shell in 4K. So, yeah, when they first asked me to kind of do a standing talk, I was that desperate for something to talk about. You almost got me with the guitar singing Cold in C. If you've never heard me singing Cold in C with my guitar, just be thankful. Right, thank you very much.